Okay. So before we get into anything, does anyone have any questions about the exam or format or anything that you want to go through? Nope. Okay, well, if you do end up having a question, you can email me. Um, Also, like I sent out the practice test. If anyone has any questions they specifically want to cover on that, you can comment them or put them in the chat, and I'm happy to go through those. But I'll probably just go kind of sequentially. Okay, cool. Well, let's get started. Um, Before we get into the like new material, I included a question just going through a lot of the um, easier kind of first semester stuff that can get a little tricky when you try to think back to remember how to do it. So I'm just going to go through this pretty quickly so we can get into the more, you know, hypothesis testing questions. So basically in this, all you're asked to do is just go through each of these variables and say the type. And again, I'll try to keep an eye on the chat so that I can make sure to answer any questions. So let's say that we're just looking at cats again. The question type question doesn't really matter. This is when I had first just gotten my kitten. So I was pretty excited about cats then. I guess I decided to write about that. Um, so we have all of these variables that are about cats, and we want to figure out what kind of variables these are, whether they're numeric, discrete, continuous, or categorical, nominal, or ordinal. So the first one is birth weight in grams. If you wanted to say in the chat what you think it is, you're welcome to. I can also just go through them. Um, but yeah, I mean, it's in grams, so we know that it's going to have to be numerical. I would probably say continuous for this one. Um, yeah, yes, thank you. Coat length, we have three separate categories to it, so we know it's going to have to be categorical. In this case, I would probably say ordinal because we're going from short to long, so there's an inherent order to it. Eye size, we have kind of a score from 1 to 10. I think there's a couple answers you could say to it because for this one, because we're not given enough information. But I would probably say that that's numeric discrete, but just because, these are actual numbers and like it's very, it's about kind of the distance between 1 and 2 and 2 and 3, whether those are the same or not. And that will tell you whether it's categorical or nominal or numeric. I would probably say that this is numeric. Um, Coat color, no order to it, so it's just categorical nominal. Serotonin levels and dopamine levels are both continuous. Hopefully that makes sense to everyone. Does that sound pretty familiar? Um, cool. Okay, so now we get into the newer material where we go through what kind of statistical test we want to use with this. Um, and the question basically asks in the practice test, what if we have two groups, so two different types of cat breeds, and we want to compare these exact same variables, or three of them, birth weight, coat length, and serotonin levels, using a statistical test using hypothesis testing. So starting out with birth weight, the thing to note here is that rather than it being actual birth weight in grams, it's a categorical variable. So if we have two levels to it, right, it's either like high or low. What kind of test are we going to use? And I'll go through some of the steps here, thinking through everything. But because it's categorical and we only have two groups, we're fine to just do this with a z-test. We need to specify that it's a two-sample z-test because we're comparing two groups. And then if we list out the observations, it's just independent observations, and NP is greater than 10, n times 1 minus p is greater than or equal to 10. Coat length, again, is categorical, but in this case, we have three different levels to it. So when we have three levels to it and two different groups, that's going to have to be a chi-square test of independence. Independent observations and expected counts greater than 5. Serotonin levels, now it's continuous, two groups, so it's going to be a t-test. And we have to specify that it's two-sample independent t-test, then the assumptions. So here are the important things to remember when you're doing this, like kind of figuring out what test to use. It's not enough to just say that this is a z-test or this is a t-test. You have to specify the type. So for example, if we're going in it here, I can't just say that this is a z-test. I have to specify it's a two-sample z-test because we have two different types of z-tests. For chi-square, I can't just say it's a chi-square. I have to say chi-square test of independence because there's also the chi-square goodness of fit test. For t-tests, I have to specify one, that it's two-sample, and two, that it's independent, because again, we have paired t-tests and we have two-sample. And then there's a question in the chat. You explain why you need to make birth weight categorical. It's just the way the question was framed in the practice test. It definitely does not have to be categorical. It was just like, you know, I didn't want to make you have two t-tests. So in the practice, I was like, okay, well, let's say we make this categorical, then what test would you use? It's totally fine. Yeah, no, but that's a good question. You could definitely do a t-test here. There's no reason that you would have to make it categorical. So when we go through choosing a test, I like to go through kind of three different thought processes. So the first thing is, what is the statistic I'm working with? Is it a proportion or a mean, right? Those are kind of the two that we work with. The second thing is how many groups I'm comparing. So, you know, the statistic that we're working with will tell us whether we're working with like Z's or T's or, you know, ANOVA or chi-square. But it won't tell us kind of like within those tests which one we're using. So how many groups am I comparing if I have, oh, hey Huda, do you have a question?
Yes, hi, Abby. I would like to ask you that regarding the birth weights separated into category because we have two cat, British short hair and American short hair and birth weight. So can we do chi-square because we have two variables, categorical variables?
Yes, definitely. You can do either a chi-square or a two-sample z-test here. Yeah, great.
Okay, thank you.
Yeah, and either way is fine. They just have slightly different assumptions. So yeah, but yeah, that's a really good question. Okay. So yeah, second thing is you want to think about how many groups you're comparing. The third thing is, does this meet the assumptions? And the reason why is because we did that like last day of class where we talked about non-parametric testing. So if it doesn't meet the assumptions, and normally the assumptions that we're thinking about are either like, is it independent observations? If not, then it's a paired test, or is it smaller sample size? And then we have to work with kind of non-parametric tests. I include a slide here where it kind of goes through the different tests that you would use with different types of data. I think this could be helpful to have kind of on your cheat sheet, but you guys are also allowed to have the like inference sheet. So let me see if I can go to that. Oh, maybe I don't have it pulled up. Oh, here. You're allowed to have this sheet pulled up for the test anyways, which goes through each of the different tests, their assumptions, and what you're working with. So honestly, like you probably don't have to write it down, just because it has everything that you already need. Like here it's z-test and it tells you its proportions, like difference of two proportions or one. Um, this one is chi-square, so it tells you like you have two categorical variables versus one. So this can be used for like, you know, this lists out all the assumptions and also what the different tests are. So for your cheat sheet, I wouldn't spend too much time writing out all of this just because it's already provided for you. Cool. So moving on. I guess I was, yeah, trying to make the test kind of different than just pop health stuff. I wrote this like a year ago, so don't blame me too much. So this one's about vampires. Basically, we're thinking about like in this hypothetical world, there are vampires that exist, and we want to figure out what type of blood they prefer. Here, that's our outcome. Ooh, that's bad. Based on a ton of different variables. So we're told that the study the participants are chosen randomly from different vampire communities, and that the data was collected at one single time point. Is the study generalizable? And again, this is from the first half of the year. And yes. So I don't know how much you guys remember this, but basically like if we have a random selection, so the participants are chosen at random, it almost doesn't even matter where they're chosen from, as long as they're selected randomly, then we say it's generalizable. If we have random assignment, so where we have specific groups and people are randomly put in one or the other, then we can say it's used to establish causal relationships. So in this case, we don't have random assignment. It's collected at a single time point. So it's just cross-sectional data. We're not like assigning people to different things. So we cannot say that it's can be used to establish causal relationships, but it is generalizable. Does that make sense? Okay. So now we're asked to describe the relationship using a measure of association. And the reason I want to talk about this is because I think last year some students had trouble with measure of association and what that means. So for this class, what we mean when we say measure of association is a risk ratio, an odds ratio, or a risk difference. So you're not going to do a statistical test here. It's just talking about these like risk differences or odds differences and ratios. We consider a risk here preferring human blood. That's kind of like our outcome. And we're going to compare these two groups here. So once you kind of get that, then the rest of it's pretty straightforward. But just remember that when we say measures of association, we specifically mean one of these three. You can do any of them, but those are what we mean when you see measures of association. So for risk, we just do the total number that had the event, or prefer human blood in this case, divided by the total. So it's going to be 20 over 75 for our no, not able to transform into a bad group. For our yes group, it's going to be 35 divided by 60. And then we just divide these two numbers. Pretty straightforward. Once you have your risk ratio, which is 2.18 here, all you have to do is just describe it appropriately. And the reason why is because it can be tricky to know like whether this is a risk ratio or a risk difference if you only provide this one number. So I would just add a little like description here where you say, okay, the vampires who were able to transform had 2.18 times or 118% higher risk of preferring human blood compared to the vampires who weren't able to transform. Okay. It would be a better question on the exam where it's about something more meaningful than this made up situation. But I think the rules will all still apply pretty similarly. Okay. So now we're getting into regression, and this is a mix of some of the review from last semester and then also some new stuff. So let's say we have number of movies someone is in, and fame level. And we want to look at kind of whether there's an association between these two variables. So the first thing that you're asked to do is write out the sample equation for the estimated regression line. We know that it's for the sample because it's the estimated regression line. We see estimated here. That tells us we're in sample world, not population world. So how do we write it out? When we're thinking about the sample, it's all about predictions. So for our prediction, we have y hat. That just means it's our predicted y. And then it's going to be equal to our intercept plus our number of movies times x. So this kind of beta here times our x of number of movies someone is in. And this y is in the way here, but pretty straightforward. Important thing to remember is to label things. You just need to label, like basically say, define this y hat here and this x here. If we were talking about population regression, just remember we don't include these parameter estimates because those are never actually truly known because we're thinking about it in terms of a population. So if it was a population, it would just be uppercase Y. I'll try to write this out. Oof, see how it goes. Plus beta naught, which is just our intercept, plus beta 1 times x1. Again, you would define your x1 and y1, and then plus error. And you need to include that error there in the population regression, but not in the sample regression, because the sample regression is estimated, so we don't include error. Error is just residuals. Okay. Again, if you have any questions, you can definitely put in the chat or raise your hand. Okay, so now we want to do some interpretation. again, a little bit of review from the first half. So our intercept is just the value of y when x is 0. So in this case, we would say that when, someone is, I guess the true definition of it would be like when someone is in 0 movies, their fame score on whatever continuous scale is equal to 0.018. Is it meaningful in this case? It could be, definitely. It's definitely possible for there to be someone, a celebrity that's not in any movies. The only caveat is that you just want to know the minimums to make sure you're not extrapolating beyond our minimum. Cool. I'm going to say next semester, we will not be talking about intercepts anymore at all, just because we're going to get into multivariate regression. So in multivariate regression, they're almost never meaningful. Interpret the parameter estimate. So now we're working with this parameter estimate here. You all are pretty good at this. All it is that just for every additional movie someone's in, their fame score increases by that amount. Pretty straightforward. Okay, here's where we get into the second half. Does this meet the assumptions of linear regression? Important thing to note here is that the plots we're going to look at are this one here in the corner and this one down at the bottom, if it'll even let me underline it. So another thing that I'm going to look for, like as I'm grading, is not necessarily whether you have the exact same answer as me. Like if you say something is non-linear and I think maybe, hey, it kind of like looks linear, like there's no clear pattern, as long as you provide a good justification, I'll still probably give you credit. So just make sure you have a good justification, or even just say like, there's no pattern or there is a pattern, and that should be enough. Don't stress too much about getting it exactly right. So in this case, let's start with the linearity assumption. Cloud of points, no clear pattern, probably met. The same plot is used for our kind of homoscedasticity assumption, which is the equal variance assumption. In this case, we would see an exaggerated fan shape. For this question, when you talk about the line assumptions, I'm looking for you to explicitly say exaggerated fan shape or something similar. So just make sure to write that. And it'll spread out like this. So you'd have like clustered points here, just all close together at the beginning, and then they'd spread out towards the end. Independence is the same for almost everything. It would just be, there's no reason to think that, number of movies would be non-independent between different observations. In this case, again, like you could say that this might not be met. You could be like, well, it's reasonable to think that maybe some of the movies people are in are the same, and then they might be correlated observations. That's totally fine. I just want to see a good justification. Normality of residuals, this is where it gets a little tricky. Like this here doesn't look super normal to me. You kind of can see this like bimodality. So I might say that this is like not super met for the residual normality assumption. So cool. Now we get into outliers and leverage points. And this is tricky because I think it's important to remember what we're looking at when we think about outliers and leverage. Because if you look at this plot down here, Cook's D, we do see some influential points. Yeah, but we're not thinking about Cook's D. We're not asked about influential points. We're asked about outliers and leverage points. So when we go through and look at these two plots here, there aren't any that are beyond our thresholds of 2 and around like 0.9 or 4p over n, 2p over n. So in this case, there aren't any. Yeah, and that's all you need to say. So, okay. So we've gone through a little bit about choosing an appropriate tests. This is just another example of doing that. And also remembering to include not just that it's a t-test or not just that it's a z-test, but it's two sample versus paired versus, independent, etc. Okay, so the first one, we say it's average time. So that tells us that this is probably going to be a continuous variable at 3 different schools, 3 different groups. 3 different groups, we know it's going to have to be an ANOVA or a chi-square, but because we're working with continuous data, it's going to be an ANOVA. Cool. Important thing to remember about ANOVA is that the only time that we use it is when there's 3 or more groups. If we only have 2 groups that we're comparing, or kind of like if you're looking at a table, like 2 columns, none of the answers are going to be ANOVA. It's just going to be a t-test. The only time it's ANOVA is when we have 3 columns or 3 different groups that we're comparing. Chi-square is a little different because then we can only have 2 groups, but like multiple levels within that group or multiple like categories in it. Then we use chi-square, but with ANOVA, it's different because we're just comparing the proportions for like, kind of one of those rows. Okay, so that's, yeah, Harisa.
Wait, sorry, I kind of missed that. If you could
Yeah.
go back again about that chi-squared versus ANOVA when you were talking about like the 3 categories.
Yeah, and it's tricky, like it always trips me up. So basically like if we have, let me see if I can flip a table. If we have, imagine like a table 1 that we're working with. If we have 2 groups that we're comparing there, so 2 columns, then it'll never be an ANOVA because we need to have 3 different groups. It's going to be a mean of 1, a mean of a second one, and a mean of a third one that we're comparing. For chi-square, it could be 2 groups, but it'll be multiple proportions within those groups. So basically, if we have, like for the kitten example, let me see. So like in this case, we have coat length, short, medium, and long. That's 3 different categories within it. And so we're going to have to use chi-square in this case because we're comparing each of those proportions to like basically what the expected would be. So if you have 3 different groups, then it's going to have to be an ANOVA or chi-square. But if you have 2 groups, then it can't be ANOVA, but it could be chi-square. Does that kind of make sense? It's tricky.
Oh, so you're saying that in some situations where you could use chi-square, you could technically use ANOVA? Or
No.
no?
So if it's a proportion, then you're going to be using chi-square. If it's a mean, then you're going to be using ANOVA. The difference is that for ANOVA, there have to be 3 different groups that we're comparing. For chi-square, it could be 2 different groups, but we just have multiple levels of that group, so multiple categories within it. So it could be like here, coat length would be short, medium, and long, but we're technically only comparing between 2 groups. There's just 3 different categories that we're comparing within it. Like in this example, we were told basically like compare between 2 different breeds of kitten. It's never going to be an ANOVA because we need it to be 3 different groups that we're comparing for it to be ANOVA. Does that kind of make sense?
Yeah, this clarifies it more.
Okay, I can try to go through it a little bit more. Yeah, but it's a tricky idea. Just know that like we only use ANOVA if we have 3 or more groups that we're comparing. Okay. Let's see. Yeah, so the second one is another one of chi-square, where really we're only working in like, yeah, I guess in this case it'd be different groups that we're comparing. Yeah, so we'd have different like groups of number of taste buds. So that's what each of these are. And then we're comparing the proportion or preference, so it'd be percent for a new ice cream flavor. So it's going to be a chi-square. And then yeah, the rest of them are pretty straightforward too. Like this one is just before and after. Anytime you have like pre-post, it's going to have to be a paired t-test. And yeah, most of the examples we'll work with are like pre-post tests. I guess it could also be like if it's siblings that you're looking at, there's some level of correlation between the different observations in either group, then it can be paired t-test. Four is three different types of fertilizer. So we have three different groups here and different growth rates. So again, because we have three groups, it has to be ANOVA. And then the next one is difference in average monthly expenditure on groceries. So again, a continuous variable, but in this case, we only have two groups that we're comparing, so it's going to be a t-test. Does that make sense?
Yes.
Okay, so now we get into the testing. This one's is, well, we can go through, yeah, Huda.
Can you show, please, the previous slide? So why the can you explain the second one and why the fourth one is ANOVA, not chi-square? Because we have growth rate. So that's mean that we have proportion. And for three categories. So it should be chi-square, goodness of fit.
Yeah, that's a good question. I should not have included the word rates here. Rates are very confusing and like, yeah, you don't technically know, like, is this a rate in terms of like a change over time where it's kind of a continuous value, or is, people use rate to describe a proportion of something. You would not see the word rates on a test just because it's so it varies in terms of what people mean by it. So yeah, if this meant a rate in terms of like the way a lot of people use the word rate as a proportion, then it would be chi-square. But yeah, you wouldn't see rates on the test. That's a good question.
Okay, thank you. And can you explain again, please, number two?
Yeah. So number two, it's tricky because like, right, these are numbers technically, but what we're doing with it is we're categorizing people into one of these three different groups. And then we're saying preference, so like proportion of people that choose a specific flavor. Preference could be measured in different ways. So I could understand like a justification for like, hey, if we're measuring preference as like a preference scale, and maybe that's continuous, like you could argue for it being, an ANOVA. But I think like, yeah, I would see preference as like being like the proportion of people that choose different things, but I think that it would also be correct to say an ANOVA. Does that make sense?
Yes, thank you.
Yeah. And again, like if I'm grading, at least for the take home part, I'm really just looking for like a good justification, and making sure that you understand the ideas. So if you say, oh, like, preference might be measured as like, a scale and therefore it's continuous and therefore we can use an ANOVA, I would give full credit for that. Okay. So let's talk about doing some like confidence intervals. So let's say that there's a baker and they basically have this random sample of weeks throughout the year. It's 20, so their N is 20. And what they want to do is basically compare their average weekly spending, which has a mean of 150 and a standard deviation of 30, to like what their kind of population, so what their total would be over the past 5 years, which has a mean of 160. And we're told that it's roughly normally distributed. So we want a 95% confidence interval of how, based on their sample, how much they are spending on flour, or how much they are using in flour per week. So this is going to be Z. And the reason why is because like we know that it's roughly normally distributed and we're trying to approximate from a sample into the population, and we're told what the population mean is. Oh no, I'm sorry. It's going to be T because we are not given the standard deviation for it. We're only given the mean for it. Yeah. So with T, it's still roughly normally distributed, which tells us that like we can use T even though the sample size is less than 30 up here. But yeah, it's going to have to be T. So if we're talking about 95% confidence interval, there's a few steps that we need to do. The first is just calculate the standard error. The second is calculate the degree of freedom, and then use those values on the like p-value cheat sheet that you'll have access to on the exam to calculate what our critical value is. So in this case, we just do the standard deviation over the square root of n, and that's our standard error. For degree of freedom, it's n minus 1, so it's 19. And for a t-value, we just have to think, okay, well, if our degree of freedom is 19, and we have a 95% confidence interval, you would just go over to this critical p-value sheet, and you would say, okay, we are working with t. We have an alpha of 0.5 because that's equivalent to a 95% confidence interval. Our degree of freedom is 19, and then it's going to just be the two-tailed t-test because it's two-tailed because we're working with a confidence interval. That makes sense? I'm going to say like almost always in this class, you're working with the two-tailed value. Yeah, Harisa?
Wait, just to clarify, for t-test, you need the standard deviation, but you do not need the standard deviation for z-test. Okay, perfect.
Yeah, so basically like the reason that we have to use t is because we don't know the standard deviation. If we knew the population standard deviation of a sample, then we could use t, but we have to adjust for it when we don't know
Oh,
it.
wait, so if we don't know the population,
Standard
that
deviation.
means population standard deviation, we have to use T as in Tom, but Z, if we do know the population standard deviation, we
Yeah,
can use the Z.
the trick is that like in the real world, we almost never know what the population standard deviation is. So normally when we're working with means, we're working in T world. Yeah. So basically for this class, I would say, for this class, only really use Z for the most part when it's a proportion that you're working with, and use T when it's a mean that you're working with. Does that make sense?
Oh, yeah.
Okay. Cool. Okay. So now that we have our critical value, it's just the mean plus or minus this critical value times our standard error. Pretty straightforward. Our interpretation, I would literally just like copy, whatever. Copy this language on your cheat sheet. It's going to be the same every time. It's just with 95% confidence, the true average value, or if it's a difference, the true difference between these two means, between these two means, is between the lower confidence bound and the upper confidence bound. Make sense? Cool. Also include units. I mean, yeah, you're not gonna like get the whole question wrong if you don't include units, but you might get a few points off. Okay. So now we're asked to run a hypothesis test. We already have our standard error, so that's easy enough, but there's just a few more steps we have to add. So here's what you need to do when you run a hypothesis test. The first thing is to go through assumptions. So it's t-test. You would literally just go over to this sheet here, go down to t here, and you'd say, okay, I'm working with only one mean that I'm comparing to a population. So it's a one sample t-test. My assumptions are one, that the values are independent, which in this case, again, like as long as you provide a justification for your answer, it's fine. I'd say there's no reason to believe they're independent, but who knows, weeks in a year can definitely be dependent on each other, like one if it's right after the other. That your sample size is, in this case, it's less than 30, so we'd have to say less than 30, and there's no clear outliers. So yeah, just provide that text and you'll get full credit. The second thing to do is to include your null and alternative hypotheses. So the null here is work with means, so it would just be the mu of our sample is equal to the overall mean, which is 160. And then you just have to specify what those mu's are. So you'd say mu flour here is the average kilograms of flour per week. Calculating t, we already have our standard error, but we just have to do our mean minus mu, which is just When we calculate that out, we get negative 1.49. Then you plug it in. So we'd go back to our Excel spreadsheet and we would say our t is 1.49. You could also do negative 1.49, doesn't matter. And then you would look at the two-tailed t-test. Again, we're normally working with two-tailed tests. So it's 0.15. And then we just say that's bigger than 0.05, we fail to reject the null. That makes sense? Okay. So let's go through, let's do these real quick. Okay, so let's say that we are talking with someone and they say, okay, I looked at this sample. It has 150 observations, but it doesn't look normally distributed. So therefore, we should probably use non-parametric tests. How do you respond to that? And the trick here, when we think about whether we should use parametric or non-parametric tests, normally it's not necessarily about whether our sample is normal, it's about how big our sample size is. So based on the central limit theorem, if our sample size is big enough, because we're thinking about the sampling distribution and not our individual samples distribution, the sample means of all the different samples will approximate a normal distribution regardless of whether our actual sample itself is normal. So for this question, all you have to say is, because our sample size is big enough, we can say that we can still use parametric tests. Does that make sense?
Yes. Oh, I have a question.
Yeah.
I know there's like different non-parametric tests. Do we have to understand and specify all of them?
Yeah, I have a question on that. Actually, I think coming up, after this one, so we can go through it. I highly doubt you will have to, you might be asked to interpret, some p-values or something from a non-parametric test. I highly doubt you'll have to do calculations for it. So I would focus more on the calculations that you might need to do for the parametric tests we talked about. But you should know kind of just write on your cheat sheet what kind of non-parametric tests match up with parametric tests. And I have a table on that in a little bit. So yeah, talking about non-parametric tests, McNemar's test is basically what we use when we have paired samples that are dichotomous outcomes. So it's kind of like the equivalent of a paired t-test for z-tests. And we just use McNemar's test. So that's one that I would know. I would just say, all you have to know is basically we use it when we have paired samples with dichotomous outcomes. For non-parametric tests, these are kind of what the equivalents are. And I would probably just copy this table onto your cheat sheet just so you have it, because you might be asked kind of a question like this, where it's if it's non-parametric, which test would you use? So yeah, one sample t-test or two sample t-tests that are paired, you would use sign test or Wilcoxon sign rank test, then rank sum test for two samples. ANOVA is a Kirkskole-Wallace test, and then Spearman correlation for Pearson correlation. Okay. Yeah, let's get into a power question. Power questions are deceivingly tricky because I think a lot of it is really just plugging into a formula, but they do kind of seem tricky when you read it out. So let's go through this one as an example, especially because we didn't that was a remote class. But I still think it's helpful to have a practice power question. So let's say we have a population with a known mean, it's 28, and a known standard deviation. So known standard deviation, like we just talked about with t-tests, if we know the population standard deviation, we can work with z's as opposed to t's. So if we're aiming for a 95% confidence interval, that tells us we're using a critical value of 1.96 because we're working with z's. We don't have to calculate out what it is based on the degree of freedom. And we want a margin of error, a minimum margin of error of 1.36. All you have to do with this question is just plug into a formula. The formula we work with is just that the margin of error is equal to our z star, our critical value, times the standard error, which is just the standard deviation divided by the square root of n. That makes sense? I think this is trickier because like we didn't actually go through this, in person. But a lot of it, like especially with something where you're given a margin of error like this and asked to calculate a sample size, is just going to be based on plugging into the formula. So if we plug everything in, we just get 51.1. Only thing here that you'll have to keep in mind, because you won't get full credit if you say 51.1, is we can't have 0.1 of a person, right? Like we can't have proportions of a person. So if we want to meet this minimum margin of error, we have to round up. So the sample size needs to be 52. Does that make sense? Okay. There's another, let's go through this and then I want to go through another power question. But let's say we have a p-value of 0.07. What does it mean? And you're asked to select all that apply, so any that are true. So let's kind of go through these one by one a little bit. So the first is that there's a 7% probability that the null hypothesis is true. That is false. That is not what the p-value is saying, but that is a common misconception. What the p-value is actually saying is that there's a 7% probability that we would observe the data in our sample or something more extreme, given that the null is true. So we know that B is correct. That's the true definition of a p-value. Again, you can really just like copy this onto your cheat sheet to remember it, but know that something like A is not true. C should be pretty easy because we know that 0.05 is less than 0.07. And so therefore we would actually fail to reject the null, so it's not significant. And D, we can conclude that the null hypothesis is true is also incorrect. And the reason why is because we never actually accept the null. We never say the null hypothesis is true. We either reject it or fail to reject it. Okay, hi everyone. So this is where I left off on the recording. I will try to add in the later slides that I went through, so hopefully that can be a little bit helpful. But I might just end up covering them here. I'm going to try to go through things pretty quickly so that this video doesn't end up being like 2 hours long. But let's start with a chi-square question. So we know that it's chi-square because we're comparing between two groups. Here and here, group A and group B, and within those groups, 4 different categories, right? So it has to be chi-square. We're working technically with proportions, so here these are the raw counts, but when we get down to it, it's going to be proportions. So we're asked to run a hypothesis test with this data that's provided here, and we're given the test statistic for it, so we don't actually have to go out and calculate the chi-square value itself. But what we do have to do is 1, make sure that the assumptions are met, and 2, write out everything that we need for a hypothesis test. Okay, so first thing we're doing is checking assumptions. No reason to think groups are different than each other, right? These are 2 different age groups. Again, it's your justification for it. In this case, I don't see a reason why they would be related. And then the big one here that you have to check is that the expected counts are all greater than 5. This is something it's really great to actually know how to do, even though I know we haven't actually done it that much in class, but know how to calculate it out. So the way that we do that is for every single individual value here, so like 40, 60, these are our observed, we need to calculate what the expected is. And the expected is just the value here in the rows times the value here in the columns for every single individual value. So kind of like I like to imagine them almost crossing. So like imagine a line coming out here. So 100 and 130. So these ones will kind of cross at that 40. We just multiply them together and divide by the total n, and that's the expected value within that individual cell. So it would just be 130 times 100 for 40, 40 observed. It would be 100 times 150 for this kind of 60 cell. 80 times 130 for this 50 cell, on and on and on. I'm not going to make you actually calculate it here, but if you want it, they're all listed here. All of these, as you can see, are greater than 5, so we say that that assumption is met. Okay, so now we want to write out what our hypotheses are. For chi-square, we don't want to write out kind of like any kind of mathematical approximation of a hypothesis. because it's based on just whether or not there's an association between these variables. And so our null hypothesis is just that there is no association between age group and then preferred vacation destination. And our alternative is that there is an association. It's going to be that language basically every time. We're not writing out any kind of like mu, or I guess in this case, proportion is equal to anything, because it's more about whether or not there's an association as opposed to like things being equal to each other in the sense that we do when we think about if this was a z-test, for example. Now we want to figure out, well, we have the test statistic, but we want to figure out what the degree of freedom is, because that's important to, one, determining our p-value, but two, also just when you're reporting out a hypothesis test, determining your degree of freedom. Degree of freedom is the number of basically kind of columns minus 1 times the number of rows minus 1, like the number of levels in one category, and then the number of groups. If we do that, we get 3. Using our degree of freedom of 3 and our test statistic of 27.71, we can just go straight into our p critical values here, go to the chi-square, and we say our chi-square is 27.7, and our degree of freedom is 3. It's a really, really small p-value, definitely less than 0.001. And so what that means is that we can reject the null hypothesis. There's evidence that there's an association. That's all you have to list for a hypothesis test. I know it seems pretty straightforward going through it, but you just want to make sure that you have all these things, of course, including assumptions that we did before this slide. So now let's move into means as opposed to thinking about proportions. So this is more the world of t-tests. I included a lot of t-test questions on this practice exam. So as you can see, I'm not going through all of them, but question 11, I think, is a good example of something you might see on a test, except it'd probably be a little more population health relevant. So you're trying to look at whether there's a significant difference between the average height of 2 different species, 2 groups. We know that it's not going to be a one sample test. Height, so we have 15 meters and 12 meters. Those are continuous values. And these are independent samples. So it's going to be an independent 2-sample t-test. And for each of these samples, we're also getting a standard deviation, which will be helpful in our calculation, and an n. So those are kind of the important things. As I read this, I'm like, these are the things that I need to know. I know I'm doing a t-test. The first thing I'm going to do always is look at my assumptions, whether my assumptions are met. First assumption is independence. No reason to think that these aren't independent. Second, I'm thinking about the normality assumption. I say normality, but it's definitely a normality assumption. But what I really care about here is the sample size. I don't care as much about whether the actual distribution is normal, as long as there aren't any extreme outliers, because as we know with the central limit theorem, as your sample size increases, with a sufficiently large sample size, you don't necessarily have to have the perfect normal distribution of your samples. So independent observations, sample size greater than 30, and then no extreme outliers, which we're not given that here, but we are given that it's approximately normally distributed. So that should give us enough information. You're going to list out this should say HA, sorry. You're going to list out your null and alternative hypotheses. So your null is just that the means are equal to each other, or I prefer to write it out as 1 minus the other is equal to 0, because 0 is technically our null value. I like to include the null value in my hypothesis. And HA is that it's not equal to 0, so it's like, two-tailed t-test. We're not thinking about it in either direction. And now we're going to go and run through our actual t-test. So how do we do it? Well, we need a test statistic, which is just the mean difference. So 15 minus 12 is 3 meters. Now we need the standard error. And that's this formula here, where you take the standard deviation of one group over the mean of that first group, standard deviation of the second group over the n of the second group. Sorry, did I say mean? I meant n. And then you take the square root. If we do that, we get 0.616. Now that we have the mean and the standard error, all we do is just do the mean difference divided by that standard error. Technically, there's a -0 up here because we subtract our null value, but doesn't matter here, right? Because anything minus 0 is just itself. And our t is 3.87. Now, because we are working in t world, we have to calculate a degree of freedom, which is just going to be the smaller n minus 1, which in this case is 30. Sorry, I didn't mean to cross that out. So then we just go into our critical value sheet. It's 3.87 and 30. So we say 3.87, 30. Our 2 tail t-test is 0.0005. Obviously that's less than 0.05, so we reject the null that the mean height is the same, or the mean heights are the same. And that provides evidence that that there's a difference between these two. We don't know the direction of the difference, but we just say that there's a difference. If you want to be really special, you know, and get a little comment from me about doing a good job, you could also mention that this mean difference up here, that this one for group A is bigger than the one for group B, just because it provides a little bit extra context, but you don't have to do that. I just want to see a conclusion about the hypotheses. Okay, so let's say that we have all of this data in SAS and we run it and we get a t of 4.87. This is obviously a little bit different than our t here, which was 3.87. So why do we get this different value here? And the reason why is because when we work in SAS, our degree of freedom is going to be different. We are not assuming equal variance. And what that means is that we use the Satterthwaite method of calculating our 1 degree of freedom and then associated p-value. And so because that calculation is more complex, it's going to be a different t. If you're given the SAS output, you should use the p-value and degrees of freedom from that SAS output. You shouldn't calculate it on your own because just the lower one of these -1 is not going to be as accurate. Okay, let's get into ANOVAs. So we're working with an ANOVA table here. I did go through this one with the class, but I'll just run through it quickly here because this one's pretty straightforward. Really with ANOVAs, I think the important thing to know is one, know how to write out a hypothesis for it, know what the assumptions are. Again, it's all provided in that inferential statistics cheat sheet. But also I would just write out this table here in your cheat sheet just because it provides all the relevant information that you would need for anything in this table here. And it can also just be helpful context for how we get that F statistic. So if we were to write all of this out, degrees of freedom are pretty straightforward. So K is our number of categories. So we have 1, 2, 3, 4 down synthetic wool experimental installation. I don't remember writing this question. It was a year ago. So K minus 1 is going to be 3. So we have 3 for our between group degree of freedom. Then group is N minus K. Our N is 40. 40 minus 4 is 36. And then total is just 39. So it's the sum of those two. Sum of squares you're never going to be asked to calculate. And the reason why is because this formula here, these are just very, very complicated to calculate out, right? Because sigma is telling us that we need to add everything up together. So we're not going to have to do that. So sum of squares, all you have to do here is just know that this is the sum of both the within group and between group sum of squares. So it's just going to be 30-ish minus this 14. And that's going to give you, your sum of squares, which is around 16-ish. Mean square, however, you can calculate. So if you have your sum of square, it's just going to be your sum of square divided by your degree of freedom. So this one's 0.7, and then the one up here would just be 14 divided by 3. And then your F statistic is just your 2 mean squares divided by each other. So what we end up with here as you go through, these are about what we said they should be. Our F statistic is 7.94. So we have our value, and now we have our numerator and denominator degree of freedom. So what we can do is just, again, if we're running a hypothesis test, one, we would want to write out what our null and alternative are, and we want to test assumptions. Here, we weren't technically asked to do that, but if we were asked to run a full hypothesis test, we would. But it asks us if we should proceed with pairwise testing. I don't have it written out here, but that's true in the practice test. And in order to do that, we do have to figure out if this is a significant F value. It's pretty big, so it probably should be. But if we go into our p-value, p-critical value sheet, we go to the F statistic portion here. Our F is 7.94 with 3 and 34 as our numerator and denominator degree of freedom, and we get 0.0004. So that means we reject the null, can proceed with pairwise testing. So if we do pairwise testing, the question asks, how many, 1, tests are we going to run? And 2, how many, or what should our adjusted p-value be? Bonferroni corrected p-value. So the answer is just going to be in this here. So you just go and say, I'm starting out with my alpha of 0.05. I have 4 groups total. And then that's going to give me 6 total pairwise tests and an alpha of 0.0083. So that's the answer. Okay, so now we're getting into power. This is the last question. I did go through this with the class. I guess I can try to go through it again. I'm going to try to make it as simple as possible. Okay, first thing we do is we want to figure out what our null hypothesis and our alternative hypothesis. And it's especially important here to have the alternative hypothesis as well, because with power, we're not only thinking about that null sampling distribution, but also, the alternative sampling distribution. So what both would look like, assuming that they're true. Going through the question very briefly, let's say that we have 70 different households. So our N is 70, where we're testing a new algorithm. And we're comparing to the current average. So our current population average is 90 hours per month of TV watching with a standard deviation of 8 hours. So that's our population distribution, our null distribution. We want to know what power we have to detect a difference of 10 hours. We're assuming a 2-sided hypothesis test, which we almost always do in this class, and a significance of 0.05. So the first thing I'm going to do is figure out what my null distribution looks like. Okay. From that null, I'm going to then determine what critical values are needed for basically me to reject the null. Okay. I know that because I have an alpha of 0.05, that's going to be the same as, right, a 95% confidence interval. So that'll give me those 2 values if I use that 0.05 null, and then I can determine either direction that I want the alternative to be in, but we'll get to that. So we know that there's a mean of 90. So let's draw out kind of what this distribution would look like. We have a mean here of 90 in the center. And our variance is just going to be equal to the standard error, or I guess this is the standard deviation of the population, which is just, and sorry, this should be 70 over square root, 8 over square root of 70, not over the whole thing. 8 over square root of 70 is 0.338. Okay. So based on our standard error of 0.338, what threshold do we need, right, to reject our null hypothesis? So it's going to be 2-sided test. So on either one of these, basically, if this is 0.5, the sum of these 2 regions is equal to 0.5, what are these thresholds at? Same as any kind of confidence interval calculation. So if we do that, we just do 90 plus or minus 1.96 associated with this 0.05 times our standard error. And so this on this side will be 89.3. Gosh, sorry guys. 89.3, and this on this side will be 90.6. I'm just going to say 90.7. Okay. So those are our critical values. Now what we want to do is choose one of them. We can choose either. We're just saying there's a difference of 10 hours. We're not saying whether it's like more than or less than. And we want to say, if we have an alternative distribution here, right? Where does this critical value fall on this alternative sampling distribution? Like, to which we can detect this difference. So anything to the right, or sorry, to the left of this value, it's going to show up as significant if we assume that this alternative is true. So when we think about setting up this alternative distribution and finding the critical value, we use one of those values. I'm going on the lower side, like the example I just showed. And we calculate a z based on that critical value. So it's 9.73, which is pretty massive. So now we want to say, okay, basically, if I'm working on this alternative distribution and it has a mean of, right, that difference here, so that's 90 minus 10, if that is the truth, right, and we have 80 as the mean of this, and the standard error is the same, it's just 80 over 8 over the square root of 70, where does this critical value fall on this graph? And so it's going to fall, if this is 80, this 89.3 is going to fall pretty far up here. So we basically take the difference between that 89.3, that critical value, minus that mean of the whole alternative distribution, divide by our standard error to get a z, and we get 9.73. Now we want to figure out if this is 9.73, which is where it lines up with the critical value of our null distribution at which we reject the null hypothesis. It should be basically the intersect between them, sorry for my drawings. Anything to the left of this is what we want to use to calculate that power, because that's the point at which we reject the null. So just go over here. It's working in z, so it's 9.73, and we want to do a two-tailed test. Sorry, a left tail test. You're only ever working in left or right tail with your power calculations. It's never going to be a two-tailed test, at least for this class. And so it says 1, and that doesn't make sense, right? I mean, it does, because this is a really, really massive z, so it's obviously going to be really close to 1. But I think another thing I want to point out with this question is that when you put in a really big z here, right, and you get these tests that say 1 and 0, they aren't actually equal to 0 or 1, right? This 0 here is really just, you know, if you were to write this on an exam, it's less than 0.00001. And this one here is just really close to 1. We can never have it actually be equal to 0 or actually be equal to 1. Okay. So my conclusion here would just be, if the alternative is true, what's the probability of getting a value less than extreme of 9.73? And that's kind of how we interpret this here, nearly 100%. So 100% power doesn't, you know, it can't be fully 100%, but we say it is pretty close. And I hate this answer. This is terrible. Like, if you get this on an exam, like, you might honestly question your work, because you should normally get something that's more reasonable than this. But for this question, part of my reasoning for doing this was because I also didn't want you to, you know, one, like, directly plug and chug for this part B. And for this part B, you're asked, basically, let's say the sample size increases from 70 to 100. And if you go back here, you can see that it's like, it's not actually going to change from 100, because this z is only just going to increase. But theoretically, like, what would happen in any situation where we increase the sample size to power? And what ends up happening is, basically, as sample size increases, our standard error gets smaller. And, you know, you can mathematically prove that, but you can also just kind of conceptually think about that. On a mathematical scale, like, right, as our sample size gets bigger, our variance is going to get smaller. Excuse me. And so our standard deviation is getting smaller. With a smaller standard deviation, we have a smaller standard error, which means z gets larger, because this is our standard error down here. As that gets smaller, the value of z is going to increase. With a higher z, we get a higher beta. That's the probability of a type 2 error is beta. And so, you know, sorry, our power is going to increase. And so therefore beta is going to decrease. So our probability itself of making a type 2 error is going to decrease. Sorry for the misspeaking. Type 1 error, on the other hand, is based on alpha, and this is a preset value. So actually, it's not going to change based on sample size because we just set it at whatever value, normally 0.05. And like, I think, you know, the important thing I want to leave you guys with is just that, you know, we can have a sample that is sufficiently powered, has a high enough sample size to detect a really, really small difference, right? Like if we're working here, if our n, which is on the bottom here, gets like super, super, super big, then this value up here can get really, really small, right? Because this is in the denominator, the sample size is in the denominator of this formula that's also in the denominator. So if it gets really big, it's going to actually make this C bigger as well. And so, so basically, like, just because something is statistically significant doesn't mean that it's clinically significant. And what that means is that you can still basically not prove, but provide evidence for an alternative that has a really, really small difference between the null. That doesn't mean that it's actually clinically meaningful, and vice versa as well. Sometimes if you have a really small sample size, you know, you won't be able to show that these really small or provide evidence for these really small differences. And so I think that's just important to remember in statistics, that it's not the end all be all of, like, you know, whether we should do something or whether we should implement something. So yeah, thanks.